In this video, I'm going to introduce the pumping lemma for context-free languages. Just like for regular languages, we had a pumping lemma to show that 0 to the n, 1 to the n was not regular. We can show that 0 to the n, 1 to the n, 2 to the n is not context-free with a similar type of pumping lemma. So the formal definition states that there is a pumping length p, where a string w of at least length p can be divided into 5 parts, w equals u, v, x, y, and z, such that u, v to the I, x, y to the I, z are in our language or grammar for I greater or equal to 0. So notice how we're pumping v and y. And the length of v and y has to be greater than 0. So v or y cannot be empty, otherwise it'll be trivially true. And 3, the length of vxy is less than or equal to p. So we're really pumping vx and y together, but it's only v and y that are getting bigger or smaller. That x is just being maintained as a centerpiece in the middle. So here's kind of this diagram to show you what's happening. So here's u, v, x, y, and z. V and y is what we're pumping. So the first thing we can do here is we can pump it up. And pump it up, essentially what we have is we just repeat v and y by extending this center tree with another set of v and y, and then x still remains in its place. So we can keep pumping up however long we want, and this has to be in our language too. We can also pump down, so we can remove the v's and the y's, but we're still left with x in the center here. So we still have x remaining. So we can either pump up or down. And although I didn't introduce push-down automata, context-free grammars are represented with push-down automata just like finite state machines are represented for regular languages. So they work as a stack system, and that's how they can get 0 to the n, 1 to the n. So we can have a system in a push-down automata where for every 0 we encounter, we add it onto the stack, so we can have a 0, 0, 0. And then when we want to add a 1, we take the top 0 and we remove it, and then that adds 1. We take the second one, adds another 1, take the third one, adds a 1, and that's how you can get 0 to the n, 1 to the n. Well, if we think of that same thing with breaking this part into u, v, x, y, and z, think of the v's as adding zeros, and then the y's on the other side, whenever they see a 0, they convert it to a 1. So that way we can get the same number of zeros and ones. So if we pump up v, we pump up y. If we pump down v, we pump down y. And then our transition state in the middle, which we might call x, just stays in the same spot and isn't messed with, because that's what it takes to transfer from uv over to y and z. Okay, so let's take a look at this in action with a to the n, b to the n. So we can break it up into 3 parts, u, v, x, y, and z. So here I have a, b, b, b. I'm just going to bring it down as low as a, b, b, and then extend it infinitely. So I can break it into 3 parts. U, I'm going to pick u as a. For v, I'm just going to take this a. Then we have x, which we leave alone. And I'm going to pick this center a and b as x. This second b will be y, and then the third b will be z. So essentially, I'm going to increase this a and this b here. So the first thing I can do is I can move it down, so I can just be left with u, x, z, and that'll leave me with a, b, b, because I've removed the first a and the second b, or the second a and the second b. I can pump it up once, so I'll be u, v squared, x, y squared, z. And again, notice how AABB is part of the language, so this is okay. If I pump it up, I'll be left with A, B, 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 and this is also in the language, and I can go infinitely. So the point is, because there is one way, at least one way, that we can separate our string into u, v, x, y, and z such that we can pump it up and pump it down, this is a context-free language. So let's show that 0 to the n, 1 to the n, 2 to the n is not context-free. So we're going to assume that we have some pumping length p, and we're going to pick the string 0 to the p, 1 to the p, and 2 to the p to work with. Okay, now we have to split this up into w equals u, v, x, y, and z. And our choice of v and y are what we're pumping, which is important. So when we pump things up and down, we have to make sure that 0s, 1s, and 2s are being moved equally. So how can we split this string up? Well, there's really 5 possibilities. The first possibility is that we have u as some zeros in the beginning. I don't really want to focus on u, I want to focus on v and y, so we can say that v is equal to some 0, and then y is equal to 1. And because each of these are length p, we can't stretch across this whole boundary. We're just taking some v that starts somewhere in the middle of the o's and ends somewhere in the middle of the 1s. Because if you remember our earlier condition here, v, x, and y have to be less than or equal to p. So we clearly can't cover all of 0, 1, and 2. So if v is equal to 0 and y is equal to 1, then if we pump it up or pump it down, we could end up with a string like 0, p to the minus 1, 1 to the p minus 1, 2 to the p, and that's not okay, because that is not in our language still. We're looking for a 0 to the n, 1 to the n, 2 to the n. So this p here is a problem. So that won't work. The second one is, well, what if we pick v to be some combination of 0 and 1, and then y ends up being 1? Well, again, this is problematic for the same reason, but also when we pump v up, then we get 0, 1, 0, 1, which of course is not going to be in 0 to the n, 1 to the n, 2 to the n, because we have a 0, 1, and then another 0 again, so there's something inserted after that 1 that shouldn't be there. Okay, more conditions. Well, the other conditions really follow similar suit. So, other things that can happen is you can get v equals to 1, and we could also pick y equals to 1, that's fine, but then we'll end up with something weird like 0 to the p minus 1, 1 to the p plus however many we want to pump up, and then, sorry, this would be 0 to the p, 1 to the p plus whatever, and we'll end up with 2 to the p, where both 0 and 2 haven't been touched, but 1 has been pumped up. Another possible combination is we have v is equal to 1 and y is equal to 1, 2, but again we run into the same problem that we did earlier. Then of course the final possibility is that v is equal to 1 and y is just equal to 2, and then we have a repeat of the first situation where if we pump down, we have 0 to the p, 1 to the p minus 1, and 2 to the p minus 1, and then our problem here relies with this 0 to the p. So there's no possible way that we can pick v and y such that when we pump it up or down, this string stays within the language. Therefore, 0 to the n, 1 to the n, 2 to the n is not context-free. And this is problematic for syntax, because there are some German structures which I might introduce in the next video that show, or should say correspond, to 0 to the n, 1 to the n, 2 to the n. So I may touch on that. There's also some other things which I will talk about for sure in the next video that are problematic, but context-free grammar is not enough to capture human language as well. In fact, we need to go one step further. So in the next video, I'll introduce context-sensitive languages, and then we'll discuss that maybe those ones are just a little bit too powerful, and maybe there's some intermediary language that might suit syntax a little bit more. So if you have any questions, please leave them in the comments below, and I'll answer them the best that I can.